Welcome to part 19 of our Python programming series. In this session, our main focus will be on understanding the loss function in logistic regression. In the previous two sessions, that is part 17 and part 18, we looked at use cases of logistic regression. We tried understanding the relationship between linear regression and logistic regression. We also looked at sigmoid function and how it can give us the probability. And then we saw that how logistic regression serves as a binary classifier. In this session, we're going to focus more on the loss function or the cost function. We're going to talk about a logistic loss function, or it's also called as a binary cross entropy, which is used in the case of logistic regression, specifically when it is used as a binary classifier. We will also see how these loss values are computed using that loss function. We'll use the loss function to calculate that. And then there will be a demonstration where I'll be using Google Colab to do that. And we will create a loss function using NumPy library functions. So, this is what we are going to discuss in this particular session. Let us take a moment to understand what we covered so far. In the previous session, we looked at sigmoid function, which is given here y dash equal to 1 over 1 plus e to the power minus z. Y dash is the predicted label. Z is also called as a logit function. So y dash can take value between 0 and 1, which is nothing but a probability value. And z equal to mx plus c. M and c are the parameters, and z equal to mx plus c is a linear equation. And m and c will be computed during the training stage when you train logistic regression. So we get the optimal values for m and c. M is the coefficient, c is the intercept, and x is the feature. So in this case, we assume that there is only one feature. So this is what we covered during the last session. Here is the loss function or cost function used in the case of logistic regression. This is called as logistic loss or binary cross entropy loss. So this loss function differs from the loss function which we used in the case of linear regression. In the case of linear regression, we used mean square error or MSE. So we can't use the same loss function here because here we have a classification problem. So therefore, we have a different loss function, that is logistic loss or binary cross entropy. This is one of the loss functions used for classification. Now, if you look at this loss function, L of y comma y dash, so this L stands for the loss values, and this is the loss function that we have. And this function depends on two variables, y and y dash. Y is the actual label, which can take 0 or 1, and this actual label is found within the label data set along with x, which is a feature. Y dash is the predicted label, which can be found using the sigmoid function which we just saw. So this depends on y and y dash. If y and y dash are given, then we can compute the loss value using this particular function. Now, as you know that y dash can take a value between 0 and 1, which is probability, and y, which is found within the label data set, and that can take only 0 or 1 in the case of binary classification data set. So, if y equal to 0, that means this term becomes 0. So, loss value can be computed using minus log of 1 minus y dash. And similarly, when y equal to 1, this term becomes 0. Therefore, the loss function will be simplified to minus of log of y dash. So, this is how you can compute the loss values in the case of logistic regression. So, let us look at all the three functions we just saw. The first one is a loss function, which is called as a logistic loss or binary cross entropy. The second one is called as a sigmoid function, which is used to compute the predicted label y dash. And the third one is a linear function, which is represented as z, and that is also called as a logit function. Now, if you look at these three functions, So they are interconnected. That means the loss value depends on y dash, and y dash again depends on z, and z depends on m and c. If you look at this three functions, y and x are part of the label data set, so that will be provided to us. So what we are going to compute is m and c during the training stage. So m and c will be computed during the training stage. So when m and c get updated, z value changes, and when if z value changes, then y dash gets updated, and as and when y dash changes, the loss value also will be affected by this. So goal of this process is to minimize loss function, and when this is minimum, the m and c values what we get are called as optimum values. So we need to find optimal values for m and c, and that is when the loss is minimum, because the loss indicates that the loss value indicates the error between the actual and the predicted labels. So we want to minimize this gap between y and y dash. So that is possible when this is minimum, when the loss value is minimum. And to bring this loss value to a minimum, we need to update m and c in the right direction. So there's only one set of values for m and c that will give you the minimum loss value. And in order to update m and c, we have another algorithm which is called as optimization algorithm. So we will have a separate discussion on the optimization algorithm, how m and c are updated, and what are the different functions which are used to update the parameters or coefficients and intercepts. There is a well-known optimization algorithm which is based on gradient descent. We will discuss optimization algorithm separately in a separate video. But in this video, we'll focus on the loss function and how we can compute it theoretically and practically. So that we are going to have a look at it. So here, what is the essence of this discussion is, we understand that if you want to update the loss value, we need to update y dash, and that is possible by updating z, and which in turn depends on m and c. So we need to update m and c in the right direction to get a minimum value for loss function. For this exercise, I will use Google Colab. I need two machine learning libraries for this exercise. The first one is a NumPy library, and that is used to create the logistic loss function as shown here. And then I need matplotlib to plot the graphs. So these are the only two libraries which are required for this demonstration. Now in this exercise, I will not compute the predicted label using sigmoid function. So rather than that, I will use a NumPy function called as a linspace to generate 100 numbers between 0 and 1. So rather 0.01 and 0.99. So through this NumPy function, I can get 100 different values between 0 and 1 that indicates the probability values for predicted label. Because loss function depends on the true label and the predicted label. The true label is indicated as y underscore true in this case. And the true label, we can get it from the data set, and which can take value 0 or 1. And when true label is 1, we compute loss value separately. And when true label is 0, so we compute separately. And as you can see here, this is the function which we just created here. And that function requires two variables as shown here. One is a true label, and I assume that in the first case, true label is 1, and the predicted label, which I compute using this NumPy function. So 100 different values between 0 and 1. So I get a loss value for this case, and that I represent as loss underscore y1. So similarly, I compute the loss value for true label equal to 0 and with the predicted label. So I get a loss value which I indicate as loss underscore y0. So this is how I compute loss values for two different cases. The first case when true label is 1 and the second case when true label is 0. Now once the loss values are computed, so then I can plot them with respect to the predicted label. So this is the first graph. There are two graphs here. As you can see, there are two graphs. The first graph corresponding to logistic loss for y equal to 1. When true label is 1, we computed the logistic loss and that is shown here. So x-axis is a x-axis is a predicted label which is y underscore pred and y-axis is a loss value here. Now what I want to demonstrate here is if you look at this particular graph, so predicted label when it is very close to 1, the loss value will become minimum. So this is what we understand because the loss value indicates the gap between or error between the true label and the predicted label. So loss value will be minimum when the true label and the predicted label are equal or almost closer to each other.
Now let
So
us
now in this case, the true label y equal to 1. So when the predicted label also is equal to or almost equal to 1, then the loss value will be minimum. So this is what we can demonstrate. Though this is the first case, and these loss values are corresponding to true label equal to 1. So similarly, I have computed loss values for the second case when true label y equal to 0. And if you look at this, here what happens is when the predicted label is close to 0, the loss value will be minimum. Again, loss value is minimum indicates that the error between the true label and the predicted label are almost 0. So that is visible from this particular graph. So through this demonstration, I want you to understand that the loss function which computes the loss or the error between the true label and the actual label, and that will be minimum when the predicted label is close to actual label, and that is when, so this is when we get the optimal values for the parameters. In the next session we'll look at very important terms used in machine learning such as underfitting and overfitting. What are they and how you can avoid them? We'll look at regularization and what are the different types of regularization we have. We'll look at bias and variance and trade off between them. And there are other important terms that we are going to look at in the next session. Thank you so much.